Hey everybody, this is lesson 5 of unit 1 of our AP Calculus curriculum. Today we're going to talk about the idea of infinite limits. Okay, so last lesson we talked about a horizontal asymptote and what that looks like. Today we're going to talk about what a vertical asymptote not just looks like, but what the actual definition is. Okay, so with that said, let's go ahead and get started. We know that it's possible to have a function where the limit as x approaches infinity is infinity, and then, or the limit as x approaches infinity is negative infinity. An example of something like this is just the function negative x. If I take the limit as x approaches infinity of negative x, well, by substitution, we would just plug that in and get negative infinity, right? And that's fine. But what does that look like graphically? That looks like, negative x looks like a line that has a slope of -1 and y-intercept of 0. As x moves further and further and further to the right, what is the y value doing? It's going further and further and further down. Okay? So that's why it gives you negative infinity. So we know that, that's fine. But here's the question, I guess. Can a function approach infinity or negative infinity as x gets closer and closer to a specific number? So instead of x approaching infinity, we are saying, can this occur? The limit as x approaches, I don't know, 2 of a function equal infinity. Is that possible? Something along that line. Well, graphically, what does that look like? That looks like, here's 2. As x gets closer and closer to 2, the function is growing and growing and growing until it reaches infinity. It's not approaching a specific number. And then remember, for the limit to exist, for the limit as x approaches 2 to even be some sort of anything, the left-hand limit and the right-hand limit both have to be the same thing. Since this limit is approaching infinity, both sides have to be approaching infinity. So from the left, as x approaches 2 from the left, we should be seeing something that goes up like this. And then as x approaches 2 from the right, we should see the same kind of trend there. Now this should be recognizable to you as a vertical asymptote. And that's really what a vertical asymptote is. Now I'm going to go over a different kind of example than this, because this one specifically says the limit is going to be the same on both sides because the limit as x approaches 2 is infinity. We didn't just say does not exist. Okay? Now, let's take a look at the rational function 1 over x. If I were to graph 1 over x, if I were to graph this, we would see something like this. Right? You should be familiar with this function. And you should recognize that this has a vertical asymptote and a horizontal asymptote. So vertical asymptote of x equals 0 and a horizontal asymptote of y equals 0. So if we were to graph this, we can see, if we were going to look at this in terms of limits, we would say that the limit, there's a few of them, I'll go through all of them, but the main focus, well, let's go back to what we learned in the last lesson. The limit as x approaches infinity of 1 over x, so as x gets bigger and bigger and bigger and bigger, the function is approaching 0, okay? The limit as x approaches negative infinity of 1 over x, well, as x gets more and more and more negative, we see that it's also approaching 0. Now, I'm going to use a notation, so this will help you understand things a little bit. Graphically, we do see both of these limits approaching 0, but you notice that this limit is approaching 0 from above. So we would say that it's approaching 0, and then we put a little plus sign there, from above. Okay? Sometimes I'll put a plus or a minus sign out front. Technically, there's no such thing as a negative 0, but mathematically, if we think about it that way, it helps us understand what we're doing a little bit more. Looking at this guy, the limit as x approaches negative infinity is 0, but it's approaching it from below. So we would say negative. Okay? So that's kind of important. And why is that? Well, if we plug in, we end up with 1 over infinity on this guy, and 1 over negative infinity on that guy. Well, we know as the denominator gets bigger and bigger and bigger, we end up with a value that's infinitely close to 0. But thinking of the signs, a positive divided by a positive is a positive, and a positive divided by a negative is a negative. Not that there's a negative 0, but again, it's a good way to think about it, to try and wrap our minds around it. So anyways, that's from yesterday. We see horizontal asymptotes because the limit as x approaches infinity approaches a specific value. Well, what about the limit as x approaches 0 of f of x? Okay? So as the function gets closer and closer and closer to 0, what do we see? As x gets closer and closer to 0, what do we see the function approaching? Well, in this case, we would only be able to say it does not exist. Here's why. We would say, now we'll look at our left and right hand limits. The limit as x approaches 0 from the left, let me replace this with 1 over x, just so I have something more to reference. What is the limit as x approaches 0 from the left? Well, it's going down, so this is negative infinity, okay? Now the limit as x approaches 0 from the right is positive infinity. So as x approaches 0 from the right, it's way up here, okay? So positive infinity. Because these infinities do not match, we cannot say the limit is infinity. We can only say it does not exist. It's when these two agree with one another that it's kind of weird. When these agree with one another, they're the same kind of infinity, we would say infinity n does not exist, or negative infinity n does not exist. If these agree with each other and they're a specific number, like they are up here, let's say they were 2, then we would say the limit as x approaches 0 is 2, but obviously it exists. Okay? Now, with that said, you can see an example here that we have a function that as x approaches a specific value, we get positive or negative infinity out of it. So again, from the left, we see that y is approaching negative infinity, and then from the right, we see that y is approaching positive infinity. Okay? So that's just an example of the fact that you can see it. Now, remember we went through an experiment with fractions the other day to see how this works out. And you remember that as the numerator gets closer and closer to infinity, we end up with an infinity if the denominator is a constant. If the numerator is a constant and the denominator is approaching infinity, we end up with a 0, right? That's what we did the other day. But now we're going to focus on another approach. What happens as the denominator gets closer and closer to 0? Well, we would say, let's go ahead and say that we have a 0 on top and a constant on the bottom. Well, we know that. That is 0. 0 over a constant is 0. That's obvious, unless that constant is 0. But what happens if we have a constant over 0? What is that? I don't know. I don't know what to do with that. Well, let's go through our thought process here. Let's say we have 8 over 8, 8 over 4, 8 over 2, 8 over 1, 8 over 0.1, 8 over 0.01, and so on. Okay? Well, 8 over 8, you can see the denominator is getting smaller and smaller and smaller. The numerator is staying the same. So 8 over 8 is 1, 8 over 4 is 2, 8 over 2 is 4, 8 over 1 is 8, 8 over 0.1 is 80, 8 over 0.01 is 800. So you can see as the denominator gets smaller and smaller and smaller, the result gets bigger and bigger and bigger. Okay? Now we can keep going with that. If I said 8 over 0.0001 or so on, that would be 2 more zeros, 8 zeros, dotted here. 80000, so we get 80,000. And so on and so forth. As this gets closer and closer to 0, this is approaching infinity. Okay? So that's how we get an infinity out. How? When the denominator is 0, or when the denominator is approaching 0, not when it is actually 0, because then it would be does not exist. So we would say that this is going to be plus or minus infinity, depending on the sign here, and depending on which side we are approaching 0 from. So if we're approaching it from the left or the right, that's going to be a sign. and then we would say a positive divided by positive, positive divided by negative, and so on. Now, just as a side note, because I want to make sure you're good with this, remember, oops, not 8, infinity over infinity and 0 over 0 are both indeterminate. And why was that? Because this tends to be a sticking point with students in terms of wrapping their heads around it. An infinity over a constant is infinity. A constant over infinity is 0. Well, so this tells me the answer should be infinity. This tells me the answer should be 0. That is in contradiction to one another, therefore we don't know what the answer is. We've got to do something else. Here, the 0 on top tells me the answer should be 0. The 0 on the bottom tells me the answer should be plus or minus infinity. So these contradict each other. That says 0, that says infinity. Therefore, we don't know the answer right now, so we say indeterminate. But anytime you have a constant and a 0 or a constant and infinity, you get a specific number out. These are things I want you to memorize, but I really want you to have an understanding of why, and this is a good idea of understanding why. Okay? So with that said, we say if in a fraction, if the numerator is finite, a specific value, a constant value, and the denominator gets really close to 0, then the fraction approaches infinity or negative infinity. Okay? And that's why I have this note here. Don't forget to consider the signs of the numerator and the denominator, and we'll talk about that in a second. So let's go ahead and take a look at a practice problem here. We have a rational function, and we're looking for the limit as x approaches negative 5 of 2 minus x over, what is that? X squared plus 3x minus 10. X squared plus 3x minus 10. We go, okay, that's simple enough. I'm just going to plug in and get an answer. And I can, that's fine. Let's see what happens. We'll try substitution. 2 minus negative 5. Well, we know we're on the right track here because we're getting a constant value here. Since this isn't 0, well, then we can't have indeterminate, or since this isn't 0 or infinity, we can't have indeterminate. So we'll plug this in. We get negative 5 squared plus 3 times negative 5 minus 10. And then simplify that, we end up with 2 minus negative 5 is 7. That's going to be 25 minus 15 is 10. Minus 10 is 0. Interesting. 7 over 0. We just talked about this. If the denominator is 0, we know that this is going to be infinity. Now, we do have to be careful here with the signs here. We don't know if it's going to be plus or minus infinity because there's a lot going on here. Now, granted, the top's positive. The question is this approaching 0 from the left-hand side, or sorry, from above or below in a sense? Is this value approaching 0 from the negative side or the positive side? So I'm going to approach this through the idea of factoring. Even though we have kind of an idea here, factoring is going to give us a little bit more clear form. Now this is, I got 2 minus x, I don't like that. So I'm going to go ahead and factor out a negative 1 on top. So I end up with negative 1 times x minus 2. And then on the bottom, that factors 2, x and x, and then that would be 5 and 2. That would be positive and negative. So we can see that we have these two things reducing each other. So we can say that the limit of this guy is going to be the same as the limit of this guy. And because those reduce, it's going to be the same as the limit of negative 1 over x plus 5. And so we can see, you should know how to graph that function. But we're talking about limits here. So if I plug in negative 5, I get negative 1 over negative 5 plus 5, which is negative 1 over 0. Again, we get an infinity. But see how that's a negative? That can cause confusion. But we still need to know what kind of 0 that is. Is that a positive 0 or a negative 0? Well, the way we determine that is based on left and right hand limits. So if I were to say the limit as x approaches negative 5 from the left of negative 1 over x plus 5, that's going to look a little bit different. And this is where you kind of got to wrap your mind around this. If I'm approaching negative 5 from the left, so here's negative 5, right? So what's a number to the left of negative 5? Well, negative 6, negative 5.5, negative 5.1. Whatever it is from the left, I'll just arbitrarily pick a number that's close to negative 5 from the left. Let's say negative 5.0001. Okay? That is from the left. you can see what kind of sign you get as a result of it. Not that you really want to plug in that number there, but we can see what kind of sign we get. So we have a -1 over, this is going to end up being a negative value. So we would say 0 from the left. I mean, I guess sometimes I'll put a -0 out front, but 0 from the left. And you can now see the sign of this. A negative divided by a negative is a positive. So the limit as x approaches -5 from the left is positive infinity. Let's go ahead and take a look at from the other direction. -5 from the right. Well, -1 over x plus 5. Again, if I plug in just -5, I end up with -1 over 0, and I don't know what kind of 0 that is essentially. Okay? So it's important that we're paying attention to this here. So what's a number that's really close to -5, but it's approaching it from the right? So here's -5. We're approaching it from the right. So that would be like -4, -4.5, -4.1, -4.0. Sorry, -4.5, -4.9, -4.9999. So I'll go ahead and put that in there. -4.999 as my example. So what kind of sign am I going to get down here? I'm going to end up with a positive sign, right? Because that's bigger than that. So we end up with -infinity. So now we can see that from the left we get positive infinity, from the right we get negative infinity. And in fact, this kind of gives us an idea of what the graph looks like. We know, and we'll get more into this in a second, that as x approaches -5, from the left-hand side, we're getting positive infinity. So from this side, we're growing. And then from this side, from the right-hand side, we're going towards negative infinity. And so you can see, actually, we have a vertical asymptote here. Now, you've also dealt with a lot of rational functions. You should recognize that x minus 2 and x minus 2 reduce. So therefore, at 2, you have a removable discontinuity. We'll talk more about that in the future. The point I'm trying to get at is this. And so what can we say is a final answer for the limit as x approaches -5 of whatever our function is? I'll just call it f of x. We would say it simply does not exist because these infinities don't match. If they did say infinity, infinity, then this guy would be coming up like this, and you say the limit is infinity and it does not exist. If it said negative infinity, then this guy would be going down like this, and we'd say the limit as x approaches -5 f of x is negative infinity and does not exist. But because these infinities don't agree, the answer is just does not exist. So that's what I mean by checking the signs of your numerator and denominator. And this one tends to be the sticking one. If I'm coming from the left, I pick a value that's close to -5, but on the left-hand side of it. And so that's why it's important to know your number lines. If I'm going from the right, what's a number just to the right of -5? That's really close to it, so -4.999 and so on. Okay, so that is the approach here, and you can kind of see that the x minus 2 is reduced there, so we end up with that, and then we get 1 over 0. Again, is that a plus or a minus 0? That's why we need to consider the signs. So we're going to check our left hand, and we end up with a positive infinity. We're going to check our right hand and end up with a negative infinity. I know the notes don't really explain why it's this, but hopefully this helps out. All right, with that said, remember yesterday we learned that if a limit as x approaches positive or negative infinity of a function approaches a constant value, then you get a horizontal asymptote. A horizontal asymptote. Okay? Today we're going to flip that. So let me go ahead and write this down. If we have the limit as x approaches plus or minus infinity of a function, and we get some sort of constant out, we would therefore say there is a horizontal asymptote when, or sorry, not when, at y equals whatever that constant value is. Okay, whatever that constant value is. Now, most functions only have one horizontal asymptote, but there are some that have a couple horizontal asymptotes, and then piecewise functions could have a ton of horizontal asymptotes. Well, I guess they can only have two. You can only have up to 2 horizontal asymptotes because you're only taking 2 types of limits. All right, so that's a horizontal asymptote. A vertical asymptote, let me go ahead and write this down. Vertical asymptote is this. If the limit as x approaches a constant number gives you plus or minus infinity, then we have a vertical asymptote, okay? So, basically what we're saying here, let me summarize it in a nice clean way. The limit as x approaches a constant is equal to plus or minus infinity, then we get a vertical asymptote. When x equals whatever the c value is. So notice what happened here. All we did was we took the x approaching an infinity and the result being a constant and flipped those. So as x approaches a constant, we get plus or minus infinity, and then we get two different types of asymptotes. This is the definition of the two specific types of asymptotes that we have. Whatever you learned in the past tends to be more of like, okay, let's just understand it graphically, and then let's look for kind of a trick that we can use to identify them analytically. So what can we see in the equations to identify these two types of things? And there was the Bono and Botno and stuff like that if you were introduced to that idea. But those are just quick tricks. This is the actual definition of horizontal asymptotes and vertical asymptotes. So yes, you want to commit it to memory, but you guys know me. I appreciate memorization, but the more important thing is to understand why. And so if you can graph these things, you're much better off. If you can visualize what's happening in your head and really understand why this is true, you're much better off. And so here is my quick look at what we can kind of summarize for this. Okay? Maybe we have a graph that looks something like this. Okay? And let's call this 3. Let's call this -2, and let's call this 4. Now you can see that we have 3 different asymptotes here. So we would say the limit as x approaches infinity of f of x is, as x approaches infinity, is 4. Therefore, horizontal asymptote, right, at y equals 4. The limit as x approaches negative infinity of f of x equals -2, right, out that way. Therefore, we also have a horizontal asymptote at y equals -2. Now this, the limit as x approaches 3, now notice we don't have the same limit. From the left it's approaching negative infinity, and from the right it's approaching positive infinity. So we would say the limit as x approaches 3 from the left of f of x is negative infinity. And you could also say the other one, but therefore we have a vertical asymptote at, or when x equals 3. Okay? So that's an example of the graph, but again, the definition is the important part, not just quick tricks, but definitions and really understanding why that's true. Now, let's go ahead and take a look at a practice problem where this will be played out. So we are looking for, well, first of all, we're just looking to evaluate the limit as x approaches 1. So we have g of x is equal to x squared over x minus 1 cubed. Okay? And we are looking for the limit as x approaches 1 of g of x. So I'm going to write the function out just so that it's easier for me to see. Now again, remember the first thing we want to do is we want to try and substitute. So we end up with 1 squared over 1 minus 1 cubed. Okay? Now the top is 1, the bottom is 0, but remember we have to check signs. The numerator, because that's squared, that's always going to be positive no matter what. Even if it said 0 squared, we would say that it's approaching 0 from the positive side, or the numerator is approaching 0 from the positive side because the square. So we know that this guy is going to be a positive. This guy, we got 0, And then we are actually, let me put the cube there, 0 cubed. Well, when I cube something, I could get a positive or a negative number depending on what kind of 0 I have. So that's why we have to check the left and the right hand limits. So let's go ahead and do that. The limit as x approaches 1 from the left of x squared over x minus 1 cubed. Well, that would be 1 from the left, I guess, squared over 1 from the left minus 1 cubed. Well, anything squared is positive, so that's just 1, so that's good. The bottom, you have to start thinking about what kind of sign I'm going to get here. So what's a number that's just to the left of 1? And in fact, you can pick any number to the left of 1. It could be negative 75 because that's to the left of 1. We're not actually evaluating the numeric answer, we're just looking for the sign in this case. We know that 1 minus 1 is 0, and 0 cubed is 0. But we need to know the sign. So what's a number to the left of 1? Well, 0 is to the left of 1. So what's 0 minus 1? That's negative 1. And what's negative 1 cubed? It's negative 1. Now again, the answer is not negative 1, but it is a negative answer. We know the final answer is 0, it's just what kind of 0 essentially. So positive divided by a negative is negative infinity. And then we'll check the other one. The limit as x approaches 1 from the right of x squared over x minus 1 cubed. And so we plug in 1 from the right squared, and then 1 from the right minus 1 cubed. Well, a positive 1 squared is a positive 1, so that's easy. Now we need to pick a number to the right of 1. So what's in, well, let me go back. 1 minus 1 is 0. We know that. Okay, and 0 cubed is 0. We're just looking for signs now. A number just to the right of 1, well, that's like 2. Or you could say 1.00001. It doesn't matter what you use, we're just looking for the sign. So 1.00001 minus 1 is 0.0001. It's a positive number. The bottom line is it's positive. When we cube a positive, we get a positive. So positive divided by positive is a positive. So we can say, as a result, the limit as x approaches 1 of g of x does not exist for 2 reasons. You're getting infinities, but in this case, the more important reason is because the infinities don't match. Okay? So that's our limit. That's our limit. Okay? So we're going to use substitution. We get 1 over 0. We've got to check our signs. So we're going to get a positive over a negative in the first case for the left, and then a positive over a positive for the one from the right, and so we end up with positive infinity. As a result of this, because the limit as x approaches 1 from either the left or the right gives you any kind of infinity, we can say that there is a vertical asymptote when x equals 1. Okay? These don't have to match signs as long as they are some sort of infinity. Now I know I didn't ask that specifically in this practice problem, but that was the point that I was trying to get at. All right, with that said, we're going to go ahead and look at another example here. This one's kind of fun because it throws trig into the mix, so that's cool. The vertical asymptote of h of x equals tangent of x. So we are looking for vertical asymptotes. Well, vertical asymptotes occur when the limit as x approaches some constant value from the left or right of the function equals positive or negative infinity. Okay, so that's the definition. So here's the question. How can I get infinity out of a number? How can I get infinity out of a number? The bottom line answer in terms of asymptotes is when you're dividing by, remember when you're dividing by 0. If you can get a constant on the top and a 0 on the bottom, that's going to approach plus or minus infinity. Okay? So anytime I say look for a vertical asymptote, you're looking for when the denominator is 0, because that's what's going to cause the infinity at a constant. So denominator, there's no denominator. It's not a fraction. Well, you should recognize that as a trig identity. How could I rewrite tangent of x as a fraction? Well, remember, tangent of x is sine of x over cosine of x. Now we have a fraction, right? So we are looking for the limit as x approaches some constant from either side, of sine of x over cosine of x to equal plus or minus infinity. How do I get that? We can conclude that would be when cosine of x equals 0, because any number up here divided by 0 is going to give us an infinity of some sort, plus or minus. So our question is, when does cosine of x equal 0? And this is where your unit circle really helps out. When does cosine of x equal 0? Well, cosine of x equals 1 at x equals 0. As we come up here, this is going to be when x equals pi over 2. And then we would say, what is that, 3 pi over 2. Okay, so up here, and down here, and then keep going up here. So that's going to be 5 pi over 2, and 7 pi over 2. And actually it keeps going, right? It keeps going, because if I look at the cosine function, when does it equal 0? It equals 0 here, 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 and so on and so forth, and everywhere negative as well, right? All these different places negative. And now, but thinking back to tangent, this is kind of cool. If I think back to the tangent graph, you remember that the tangent graph looks something like this. And we actually have vertical asymptotes at different x values. Well, where are those vertical asymptotes? This vertical asymptote correlates with this 0. This vertical asymptote correlates with this 0. And then this vertical asymptote correlates with that 0. So you can see that the vertical asymptotes are when cosine of x equals 0, because we would be dividing by 0, which would produce a positive or a negative infinity. Now again, we don't care about what the sign is. From the right-hand side it's positive, and from the left-hand side it's negative. So we can write it like that. That's probably not the most efficient way of writing it. So let's go back to the lesson here so we can see what maybe the most efficient way of writing it is. And that's a better graph of the cosine function anyways. Remember, we could do the inverse trig, but when you do inverse trig, that kind of limits your domain, and we don't want to do that. So I just like thinking of it as, when does cosine of x equal 0? That's the easiest way for me. And again, all the negative values. But we could write it like this. We could say, let k be any odd multiple of pi over 2. And so we would say, then the answer is k, right? So as x approaches k, where k is any odd multiple of pi over 2. So if I took pi over 2, essentially, and multiplied it, k is an odd multiple of pi over 2. And so our answer is k if we define it that way. I don't really care if you define it this way. More often it's just look for specific values, and so the negative versions of that as well. But you can see if I plug in a 1, we get pi over 2. If I plug in a 3, we get 3 pi over 2. If I plug in a 5, 5 pi over 2. If I plug in negative 7 pi over 2. And that would be part of that answer as well. All right, so we would say vertical asymptotes occur when x is any odd multiple of pi over 2. All right, here is your practice problem. Find the vertical asymptotes of cotangent of x. Pause the video, see if you can come up with an answer. When you're done, come back and see how you did. All right, so we have cotangent of x, and we are looking for vertical asymptotes. So vertical asymptotes occur when the limit as x approaches some constant from the left or right of the function is equal to plus or minus infinity. Well, again, how do I get plus or minus infinity? I get it when I'm dividing by 0. So I'm just going to first write g of x is equal to a fraction. Well, what fraction is that? Tangent is sine over cosine. Cotangent is cosine over sine. Okay, so again, trig operations are kind of important here. So when do I get the limit as x approaches a constant give you infinity? When the denominator is 0. So I'll set sine of x equal to 0. And we know that sine of x is equal to 0 when x equals 0, when x equals pi, 2 pi, 3 pi, and so on. Also negative pi, negative 2 pi, negative 3 pi, and so on, right? So in this case, we would say that the k value in this sense would be any whole number multiple of pi. So we could say we have a vertical asymptote at any whole number of pi. All right, so let's go ahead and, let's see, we did the cotangent one. So the vertical asymptotes of cotangent are when sine is equal to 0. And so we would say basically vertical asymptote occurs whenever x is a whole number multiple of pi. What's in the lesson here is not completely accurate. Any multiple of pi, well, I can multiply by pi by 2.784 if I wanted to, but hopefully you get the idea there. All right, last problem, it says let f of x equal x minus 1 over x squared minus 1, and we want to determine the limit as x approaches 1, negative 1, infinity, and negative infinity, and then we want to graph the function. So let me go ahead, you guys go ahead and try this, and then come back and let's see how you did. All right, we got f of x equals x minus 1 times x squared minus 1. Now, I know you guys have done stuff like this in the past, again, kind of using quick tricks to graph it, but again, I want to look at it through the actual definitions and the idea of calculus. So we are looking for the limit as x approaches, let's do the first one, 1 of f of x. So x minus 1 over x squared minus 1. Okay. Remember, anytime you write a limit, you always have to have an argument. You always have to have something there that you're taking the limit of. If you write it like this, no matter what, I'm going to mark off a point. You've got to have an argument. Okay, so remember the first step is to plug in. In this case, substitute 1 minus 1 is 0, 1 squared minus 1 is 0, 0 over 0 is indeterminate. What's the next step? Well, we try factoring. So limit as x approaches 1 of x minus 1 over x minus 1 times x plus 1, that's a difference of squares. And that's a good thing because those reduce. So we're left with the limit as x approaches 1 of 1 over x plus 1. When I plug in 1 here, I get 1 half. Okay, so that's my limit there. Now we'll go on to the next part, the limit as x approaches negative 1. Well, again, we always try substitution. Granted, we could use the reduced form, but I always like using substitution first. It just, especially when you get an answer out of it, okay? And again, it's going to help out in future concepts. Negative 1 minus 1 is negative 2. Negative 1 squared is 1 minus 1 is 0. Interesting. So what does this mean? This means we get some sort of infinity. But remember, when you talk about infinity, you've got to check signs. So what we're going to do is check our left-hand limit as x approaches negative 1 from the left, of x minus 1 over x squared minus 1. And because I'm looking for signs, quick ways of doing that is to go to the reduced form. So we end up with the limit as x approaches negative 1 from the left of 1 over x plus 1, plugging in negative 1 from the left. Again, pick a number just to the left of negative 1. Negative 1.0001. We're just looking for the sign here. We know that this is going to be 0. Negative 1 plus 1 is 0. What kind of sign? Well, because negative 1 from the left, like negative 2, negative 3, negative 4, is bigger than that, we know that we're going to get a negative answer here, so we end up with negative infinity. And then looking for the limit as x approaches negative 1 from the right, we're going to do the same thing. Let me move it down here. Okay, my brain's not working. Limit as x approaches negative 1 from the right, well, that's going to be 1 over negative 1 from the right plus 1. What's a number just to the right of negative 1? Like negative 0.009? Sorry, negative 0.999. But the bottom line is we know that's 1 over 0. Because this number is actually a little bit smaller than that, this is going to be a positive 0. And so we end up with positive infinity. So we can see that we have two different infinities. Therefore, it's not just a matter of infinity. It's going to be a does not exist. Okay, not infinity, but just does not exist. All right, the last thing we need is the limit as x approaches infinity of x minus 1 over x squared minus 1. And remember we plug in infinity. we're going to end up with indeterminate. Infinity minus 1 is infinity. Infinity squared minus 1 is infinity. That's indeterminate. So we can try, because this is infinity, we can try our dividing by the highest power. So I'm going to divide by x, actually x squared on both of them. So I end up with the limit as x approaches infinity of 1 over x minus 1 over x squared over 1 minus 1 over x squared. Then when I plug in infinity, the signs on this guy are pretty simple because infinity is a positive infinity. Okay. Remember, 1 over infinity is 0. I'm running out of room here. 0 minus infinity squared is infinity. 1 over infinity is 0. It's positive, so it's minus there. That's fine. 1 minus 0. So we end up with 0 over 1, which is 0. Okay? So we can put some boxes around here so we know. And the last one we need to do is the limit as x approaches negative infinity of x minus 1 over x squared minus 1. Again, plugging in negative infinity is going to give me indeterminate, so I'm going to use the same thing. And I'm going to go ahead and skip, well, I'll write it down. Limit as x approaches negative infinity of 1 over x minus 1 over x squared, all over 1 minus 1 over x squared. Plugging in negative infinity now, we get this. Okay. And so 1 over negative infinity is 0, but it's a negative 0. Squared is positive, so that's just going to be minus 0 over 1 minus, that's going to be 0 again. Sorry, infinity, so that would be positive 0. So again, we end up with 0, so we got that. Okay. So now we have everything we need to graph this function. Okay. We know, because as the limit as x approaches 1 is 1/2, okay, so we'll say that this is 1/2, and this is 1. Okay, we know that it's got to kind of go through that point. We know that as x approaches -1, as x approaches -1, because we got infinity and negative infinity, we actually have an asymptote there. And from the left-hand side, we're going to negative infinity, so we're going to be going down like this. And from the right-hand side, we're going to positive infinity, so we're going up like that. Then the limit as x approaches infinity, so as we go out this way, we're going off to 0, so it's going to be like that. And as x approaches negative infinity, we're going out to 0, so it's going to be like this. So we know that's kind of the idea. We do have what's called a removable discontinuity here because we removed it. We'll talk more about that in the future. But that is our graph, and then we have that horizontal asymptote there as well. All right, so that wraps up this lesson. Let's see how I did here. Yeah, got our left and right hands. We got our 0 from both sides, in a sense. And then we can see that. In the lesson, I didn't explain the kind of 0. I guess I should have done that. Here, 0 minus this 0 is actually bigger than this 0 because we're taking this denominator and it's really big. So this is even a smaller 0 in a sense than that 0 is. This guy, this is smaller in the sense, but this is a negative 0. Since this is smaller, this 0 is smaller than that 0, this 0 wins out, so it's actually, the top becomes negative 0. So so that would actually be 0 from the left. And that's why negative infinity, not from the left, sorry, from below, from negative, so that's why it's below. And this one's above. All right, anyways, that's the end of this lesson. If you have any questions for me, please feel free to reach out and get the help that you need. Otherwise, we will see you again later.